Welcome back to the deep dive. Today we are staring into the abyss. And I don't mean the philosophical one, I mean the one that lives right there on your laptop screen. You know the one. You open a file, you're expecting a nice tidy list, and instead you get the wall.
The dreaded wall of data.
44 rows, 27 columns, just a sea of numbers staring back at you. And usually when I see that, my brain just performs a hard reset. I check out. But today we are talking about multivariate data, which I admit sounds terrifyingly technical, but if I'm reading these sources right, it's basically just the art of dealing with that exact feeling of overwhelm.
That's actually a perfect way to frame it. That overwhelm is, well, it's the fundamental problem of modern research. The world isn't simple. It's not just X causes Y. It's more like X causes Y, but only if Z is happening and Q is, acting weird. When you look at a spreadsheet with 27 columns, you're looking at 27 different dimensions of reality all at once. The human brain. It's just not wired to see patterns in 27 dimensions.
So our mission today is to find the tools that let us see the invisible. We're going to crack open the toolkit researchers use to distill that massive complexity into something that actually tells a story. And looking at the roadmap, it seems like we have two main ways to attack this monster. We can explore it, or we can try to predict it.
Exactly. Those are the two big buckets. You have clustering, which is the unsupervised approach. That's pure exploration.
Unsupervised meaning we don't know the answer yet.
Right. Imagine you dump a giant jar of coins on a table. You don't know what currencies are in there. You just start sorting them into piles based on what looks similar. These are silver and small. These are copper and large. You're letting the data tell you what the groups are.
Okay, so that's clustering. And the second bucket is classification.
Yes, supervised classification. That's where you already know the answers. You know you have quarters and pennies. Your goal is to train a machine so that if I hand it a mystery coin, it can tell me which bucket it belongs to.
So finding the groups versus predicting the groups. Okay, let's start with the explorers. The first tool in the kit is one I see mentioned everywhere, usually with an intimidating acronym, PCA. Principal Components Analysis.
It's the heavy hitter.
Yeah.
And while the math is complex, the concept is surprisingly intuitive if you think about shadows.
The sources use this analogy of a cube, which finally made it click for me. So let's walk through this. We imagine our data points, those rows in the spreadsheet, as little dots floating inside a clear plastic cube.
Right. To describe where any single dot is, you need 3 coordinates: height, width, and depth. 3 dimensions. Now imagine that cloud of dots isn't just random. Imagine they are actually shaped like a flat pancake, but that pancake is floating at a weird tilted angle inside the cube.
Okay, I'm visualizing the tilted pancake. I'm with you.
Do you really need 3 dimensions to describe those dots? Not really.
Yeah.
If you rotate the cube, literally turn it in your hands until you're looking flat on at the pancake, you can draw a simple 2D map of the dots. You can just ignore the depth.
So PCA is basically the mathematical act of rotating that cube to find the best angle.
Precisely. You are rotating the data to find the shadow that shows the most spread. In statistics, spread is variance, and variance is information. If all your data points are clumped on top of each other, you know nothing. If they are spread out, you can see the differences. PCA finds the angle that maximizes that information, turning a 27-dimensional problem into a 2-dimensional map.
And what I loved about the sources is that they didn't just give us the math, they gave us a killer example. This wasn't about physics or biology, it was about writing style, a fixed productivity.
This was a fascinating study. They took 44 texts. We're talking a huge range, from Alice in Wonderland to the Book of Mormon to government documents. And they didn't read them for plot. They measured them based on word endings.
27 different suffixes, teeth, miss, alligate, intiation.
So back to your nightmare spreadsheet.
Right.
44 texts, 27 columns of word counts. Impossible to read with the naked eye. But they ran PCA. They rotated the cube. And the analysis showed that you could collapse those 27 dimensions down to just 3 and still explain over 75% of the differences between the texts.
That's a huge reduction in noise. But here is where it gets really interesting. When they plotted these texts on a simple graph based on those new dimensions, the genres separated themselves perfectly.
They did. You had the literary novel sitting comfortably in the center, the religious texts clustered in their own corner. But the group that really stood out, or rather sank, was the officialese.
The government documents.
Yes. They drifted right to the bottom of the chart.
I think anyone who has ever read a tax form or a terms of service agreement feels that sinking sensation in their soul. But the data actually tells us why they sank, right? It wasn't just random.
No, it was structural. The analysis revealed that the vertical axis, the direction the government docs were sinking, was defined by the difference between native English endings and Latinate endings.
Okay, break that down for us. Native versus Latinate.
Native endings are the old Germanic roots. Tremblis, Charldum. They are punchy, direct, concrete. Children's books are full of them. Alice in Wonderland floats high on the chart because it uses these native structures.
And the officialese.
It's defined by the Latinate endings: appellation, amplification, application, verification, verification, stabilization.
It sounds educated, but it feels distant.
It creates a wall of abstraction. And PCA proved mathematically that what we call bureaucratic writing is literally defined by the removal of native English structures. It's not just boring, it's alien to the core roots of the language.
That is a brilliant insight to pull out of a raw spreadsheet. But PCA isn't the only way to rotate the cube. The sources mention a cousin of PCA called factor analysis. How is that different? It seems like they're doing the same thing.
They are very close. But think of factor analysis as the more cynical cousin. PCA assumes your data is perfect. Factor analysis assumes there's noise or error in your measurements. Because it adds that error term to the math, it's a bit more flexible. It allows for something called factor rotation.
Which sounds like a dance move, but I assume it helps us interpret the data.
It helps us find the hidden variables. When they ran factor analysis on that same word-ending data, it confirmed something profound. It found that nativeness isn't just a coincidence. It's a latent variable.
A latent variable is like a hidden dial.
Exactly. It implies that when an author writes, they aren't just picking random words. They are unconsciously tuning a nativeness dial up or down. You don't just choose between darkness and obscurity by chance. You choose them because your internal settings are tuned to Germanic or Latinate.
So we've got PCA and factor analysis for when we are measuring things. But what if our data isn't measurements? What if we are just counting categories?
That's a crucial distinction. How long is this sentence? Is a measurement. Is this a noun or a verb? Is a count. When you are dealing with counts, with contingency tables, you need a different tool: correspondence analysis.
And this is where we get to travel back in time, the study on medieval French.
This is one of my favorites. They analyzed 342 fragments of medieval French texts. But they didn't look at the words. They looked at tag trigrams.
Tag trigrams. That sounds like jargon. Let's simplify that.
Think of it as the DNA of grammar. Instead of the computer reading the night road, it reads article, noun, verb. It's looking at the sequence of the grammatical skeleton.
So they map these skeletons out using correspondence analysis. And what happens?
At first, they get a massive split between prose and poetry. That makes sense. Poetry forces you into rigid grammatical structures to fit the rhyme. But when they zoomed in on just the prose text, the map became a timeline.
This blew my mind. They didn't tell the computer the dates, right?
No dates were input. But the map perfectly separated texts from before the year 1250 and texts from after 1250.
So the math actually visualized the evolution of the French language.
It visualized the slow drift of syntax. It's like carbon dating, but using grammar.
Yeah.
And it allows you to play detective. They had some texts where the date was unknown. Historians were arguing about them. They plotted them on this map as supplementary points.
Well, ghosts in the machine.
And lo and behold, those mystery texts landed right in the transition zone, suggesting they were written right around that 1250 turning point.
So we've rotated cubes and we've made maps. But sometimes a map isn't enough. Sometimes you want to see a family history. You want a tree.
This brings us to hierarchical cluster analysis. The goal here is to build a dendrogram, a tree structure that shows who is related to whom.
You can start with the big group and chop it up, that's divisive, or start with individuals and glue them together, agglomerative. But the result is this branching family tree. And the case study here tackles a problem that had stumped linguists for a long time: the Papuan languages.
Papuan languages are a nightmare for classification. There are so many of them, and they evolved so fast that if you look at their vocabulary, their specific words, there's almost no overlap.
So you can't say, oh, they both use the word water, so they must be related.
Exactly. The word for water might change completely in just a few generations. So the researchers ignored the words. Instead, they used a checklist of 125 grammatical traits. Things like, does this language use prenasalized stops? Yes or no. Does it have a masculine, feminine gender system? Yes or no.
They looked at the operating system, not the files.
And when they fed this grammatical checklist into the cluster analysis, a beautiful tree emerged. It successfully separated the Papuan languages from the oceanic languages. But more importantly, it grouped the Papuan languages by geography.
So the languages spoken on the island of Bougainville ended up on one branch, and the ones from the Bismarck Archipelago on another.
Purely based on grammar. It shows that even when the words mutate beyond recognition, the grammatical skeleton remembers where it came from. It retains the history of the migration.
But I have to ask the skeptic's question here. If you feed enough random data into a computer, it will eventually find some pattern, right? How do we know this tree isn't just a fluke?
That is the single most important question in data science. And the answer is bootstrapping.
Which implies pulling yourself up by your shoelaces.
In statistics, it means resampling. Imagine taking that checklist of 105 traits for the languages. You scramble the list, pick a random handful, and build a tree. Then you do it again and again, 200 times.
So you're basically checking your work over and over again with slightly different variables to see if the result holds up.
Exactly. You look for stability. If a specific branch, say the Bougainville group, appears in 95% of those scrambled attempts, you can trust it. It's robust. In the Papuan study, the deep ancient history was a bit fuzzy, but those geographic groupings were rock solid.
Okay, so that covers the exploration side. We've found groups we didn't know existed, but I want to pivot to the other bucket you mentioned at the start, prediction.
Supervised learning. This is where the game changes. We aren't asking what patterns are here. We're asking, can we build a machine that makes decisions for us?
And the tool for this is cart classification and regression trees, which, let's be honest, is a fancy name for a flowchart.
It is a flowchart, but one generated by an algorithm. The example they used is something we do in English every day without thinking. The dative alternation.
Give us the example.
You can say, John gave Mary the book, or you can say, John gave the book to Mary. Both are grammatically correct. But why do you choose one over the other in the moment?
I honestly don't know. It just sounds better.
Sounds better is actually your brain running a complex variable calculation. They fed thousands of these sentences into the CART algorithm, and it built a decision tree to predict which one a speaker would use. It found that the most important question, the root of the tree, was access of recipient.
Meaning, have we already talked about Mary?
Right. Is Mary given information, or is she new to the conversation? If she's known, the tree goes left. If she's new, the tree goes right. And then it checks other things, like the semantic class of the verb.
So it reveals the logic gate inside our heads, but the sources mention a danger with these trees. They can get too specific.
That's the overfitting problem. If you let the tree grow forever, it will create a specific rule for every single sentence in your dataset. It will have a special branch for that one weird thing John said on a Tuesday.
It's like a student who memorizes the answers to the practice test instead of learning the subject. They get 100% on the practice, but fail the real exam.
Exactly. To fix this, you have to prune the tree. You literally cut off the weak branches. You consciously sacrifice a little bit of accuracy on your training data to make the model simpler, because simpler models generalize better to the real world.
I feel like there is a life lesson there. Sometimes being a little less precise makes you smarter overall.
It's the battle between memorization and generalization. You always want generalization.
Now, for our final segment, we're bringing out the heavy artillery. The advanced detectives, discriminant analysis, and support vector machines.
These are for when the easy patterns aren't enough. Let's look at linear discriminant analysis, or LDA.
They use this to identify authors, right?
Yes. They had texts by 3 Spanish writers, Cela, Mendoza, and Vargas Llosa. They wanted to see if the model could tell them apart just by looking at the frequencies of common words.
How does LDA actually do that?
It works by looking at the means, the averages of the groups. It tries to draw axes through the data that push those averages as far apart as possible. It wants to maximize the distance between the center of the Cela cloud and the center of the Mendoza cloud.
And when they ran it, it worked suspiciously well, 100% accuracy.
And that alarm bell should be ringing.
Yeah.
100% accuracy usually means you've overfitted. It means your model has memorized the noise.
They tested this, didn't they?
They did a leave one out validation. They hid one text, trained the model on the rest, and asked it to guess the hidden one. The accuracy dropped. It was still good, 9 out of 15 correct, but it wasn't the magic 100%.
It's a good reality check. If a model looks perfect, it's probably lying to you. Which leads us to the final tool. This one has the coolest name, support vector machines, or SVMs.
This takes a completely different geometrical approach. LDA looks at the averages, the centers of the groups. SVM looks at the boundaries,
The edges.
Imagine 2 armies on a field. SVM tries to draw a line, a hyperplane, right between the front lines. But not just any line. It wants the line that creates the widest possible no man's land between the two forces.
So it's building a wall with a buffer zone.
Exactly. And the specific data points, the soldiers standing right on the edge of that no man's land, those are the support vectors. They are holding up the wall.
And when they applied this back to our medieval French friend, they found something that I think sums up this whole episode.
They did. They asked the SVM to predict two things: the genre of the text and the region where it was written.
When it predicted genre prose versus poetry, it was 97% accurate. The wall was solid.
But when they asked it to predict region, it dropped to 62%.
That is barely better than a coin flip. Why did it fail?
Because the model couldn't find a wall. And that failure is actually a massive insight. It tells us that genre has rigid rules. You're either doing poetry or you aren't. But region, that's fluid. Dialects blend into each other. There are no walls in geography, only gradients.
So the tool didn't just fail, it revealed the nature of the reality it was studying.
That is the ultimate takeaway. Whether we are rotating cubes with PCA, drawing family trees with clustering, or building walls with SVMs, we aren't just crunching numbers. We are testing our intuition against reality.
We thought officialese sounded stuffy. PCA proved it's because of the Latinate endings. We thought Papuan languages were unrelated. Clustering showed us their histories and their grammar, not their words.
These tools allow us to verify our theories. But we have to remain skeptical. As we saw with the Spanish authors and the decision trees, you can force a model to fit anything if you try hard enough. You can always memorize the noise.
The challenge is finding the signal. So the question I leave you with today is this. When you look at a chart or a prediction in your own field, are you looking at a robust, prune-tested truth? Or are you just looking at a model that has memorized the practice test?
It's a fine line to walk.
Next time you open that massive spreadsheet, don't panic. Just remember, rotate the cube. Thanks for listening to The Deep Dive. See you next time.